Hello everyone, welcome to Math with Allison. Today we're continuing our series on derivatives, so specifically we're talking about concavity. So let's go ahead and dive into it. So question of the day, what is concavity? So I have a beautiful function right here, f of x equals x cubed, and really concavity is the curvature of the function. And there's only two options for concavity. There is concave up like a cup, concave down like a frown. So let's go ahead and look at the concavity of this function. You can think of it literally as up and down. So if we start at this first part, let's start at the bottom right here. We actually have a function that is concave down. Do you see how it is curved downwards? And then we have what is called a point of inflection, and that is where it changes concavity because as we can see on top, the function is actually concave up. So it curves upwards. So what does this have to do with our derivatives? In order to find if a function is concave up or down, we actually need to look at the second derivative. So let's go ahead and calculate that of our function. So we have f of x equals x cubed. F prime of x is going to be equal to 3x squared. And now our second derivative, f double prime of x, is going to be equal to 6x. So very similar to intervals of increasing and decreasing, what we do is we set this equal to 0 and we solve. So if I divide both sides by 6, I get x is equal to 0. And whatever x values we get are the inflection points. And if we look at our picture, right, we have an inflection point at x equals 0. So also very similar to the first derivative test, we have to draw a number line. And so we label our inflection point, and then instead of f prime on top, we have f double prime of x, because if it's positive or negative, that tells us the concavity of f of x. So there will be a bit different way of drawing it. But of course, just like we normally do, we're going to go ahead and test some points in each interval. So let's do -1 and +1. We plug that into the second derivative. So I'm going to go ahead and do that. Alrighty, so we have when we plugged in -1, it was negative. And that means our function is concave down. It is negative, so we have a frowny face. Now on our other interval, when I plugged in 1, I got a positive value, which tells me our function is concave up, like a smiley face. It's positive, it's happy. And if we compare that to our actual function, we can see those different concavities. On the left side of 0, we have that it's concave down, and on the right side of 0, we have that it's concave up. So that is what concavity is, and I have that official definition written out right here. So f of x is concave up on some interval ab when f double prime of x, or the second derivative, is greater than 0 on that interval. F of x is concave down on ab when f double prime of x is less than 0 or negative on that interval. And then f of x has a inflection point at x equals c when that f double prime of c equals 0. So when we solve for those values. So let's just go ahead and go through some examples. We're going to identify the intervals of concavity up and down of this entire function. So first, we need to find the second derivative. So let's go ahead and do that. We have to do the first derivative. Let's go ahead and try to simplify this a little bit. We can pull out a 12, right? And we're left with 3x squared minus 2x minus 1. And let's go ahead and try to factor that. So I'm going to have two pairs. One of these will be 3x, one of these will be x, and we have to get that -2. So I'm going to assume this is a -1, and then this one's a +1. And so now I'm going to go ahead and highlight this because it's our fully factored form of the second derivative. And now we have to set this equal to 0 and solve for the inflection points. And so this is going to give me two inflection points. X is equal to 1 and x is equal to -1/3. So I'm going to go ahead and draw out the number line. Okay, let's choose our test points. I'm just going to choose -1, 0, and let's go with 2. And so I'm going to plug this into that highlighted version of the derivative. All we care about is if it's positive or if it's negative. We don't necessarily care about the value. So let's go and plug those in. Okay, this is what I mean by we don't have to, multiply it all the way out. All I care about is that this is going to be a positive value because I have two negatives. So that means this will be positive, which tells me the concavity. It is positive, it is happy, we have a smiley face. So again, here I have one negative value. This is going to be a negative interval, which tells me my function will be concave down. We have a frowny face. One more value. Again, I don't care what 12 times 7 is. All I care about is if it's positive, which it is, and that tells me it is going to be concave up. So now our next step, what we can do is, because the question is asking us to identify the intervals of concave up and down, I need to go ahead and write out my answer all officially. So I'll go ahead and write that out. Okay, so I have these written out, and let's go ahead and compare this with our actual function. So I have it drawn out right here. And now let's go ahead and look at our inflection points first. We have an inflection point actually at x equals -1/3, and so that's going to be about right here. And also at x equals 1, which is going to give me a value right here. And so now let's go ahead and look at our concavity. So just like with our number line, we have that this part is going to be concave up, but then it switches to concave down, right? There's a little bit of concave down right there. But then we immediately go back to concave up. And so that's how we can also tell from the graph, right? So let's go ahead and see another example. We want to find the intervals of concavity of f of x equals e to the x times x minus 3. So let's go ahead and do this thing. I'm going to use product rule because my first term is going to be e to the x and my second term is going to be x minus 3. Let me go ahead and set that up. Alrighty, so the derivative of e to the x is just e to the x, right? So nothing needs to change there. And the derivative of x minus 3 is just going to be 1. So when we want to find f prime x, all we have to do is cross multiply and add those together. So first I get e to the x times x minus 3. And then we are going to add e to the x times 1. If we wanted, we can simplify that out a bit more. I get x e to the x minus 3e to the x plus e to the x. And now here I can see I can combine like terms, right? I can combine these two together. And that's going to give me x e to the x minus 2e to the x. Okay, so remember, we aren't stopping at the first derivative. We need to keep going with the second derivative. So in order to find the second derivative, again, with this first term, I need to use product rule. So I'm going to go ahead and set that up. Okay, so our first derivative of f is going to be 1. And again, e to the x, its derivative is just e to the x. So we'll cross multiply and add those together. And now we can take that derivative of minus 2e to the x, which is just going to be that same thing. That minus 2 just hangs around. And boom, there we got it. If there's any combined like terms we can combine, let's go ahead and do that. It looks like that e to the x minus 2e to the x can be combined. And so that gives us x e to the x minus e to the x. So now let's go ahead and try to simplify this a little bit. I can pull an e to the x out of both terms, and my leftovers will be x minus 1. So I'm going to go ahead and highlight this so I can remember to come back to it. Okay, so remember, we have to find the inflection points, and we do so by setting that equal to 0. So if we set both terms equal to 0, first we get a inflection point at x equals 1. But if we try to solve e to the x equals 0, we're never going to find a solution, and so that doesn't give us any critical values. So here we just have one inflection point, and I'm going to go ahead and draw our number line. Okay, let's choose some values. Of course, I'm going to choose 0, and let's go with 2. I'm going to plug those into our second derivative. Okay, so first I got a negative value when I plugged in 0, which tells me my function will be concave down. And then I got a positive value when I plugged in 2, which tells me my function will be concave up. So now let's go ahead and write these out all officially. Okay, let's compare this with our actual function. So I'll zoom out, I have it right here. And first, let's go ahead and look at our inflection points. So our only inflection point was at x equals 1, which is right here. And now we can look at our concavity. So first we have a function which is concave down, but then we quickly switch to concave up. So that checks out with our number line. Let's go ahead and try one more problem. And now we have a natural log function. So we have natural log of 3x squared plus 1. So in order to find our first derivative, we actually need to use chain rule. So my inside is going to be 3x squared plus 1. And then our outside, g of u, will be the natural log of u. So u prime is going to be equal to 6x, and let's say g prime of u is going to be 1 over u. So this helps us find our actual derivative. So f prime of x is equal to u prime, which is 6x, and we're going to multiply by 1 over the inside, which is 3x squared plus 1, which if we wanted, we could rewrite that as 6x over 3x squared plus 1. We can't stop here. We need to find the second derivative. And in order to do that, we are going to have to use quotient rule. So I'll go ahead and set that up. Okay, so f prime is just going to be equal to 6, and then g prime is going to be equal to 6x. So remember, we actually need to follow an order when we get our derivative. So this will be the second derivative. We have to start from the bottom, work our way to the top. So I get 6 times 3x squared plus 1, and we have to subtract. So now we have to subtract this second cross multiplication, and that's 6x times 6x. And then all of this is divided by the denominator squared. Okay, let's go ahead and simplify this out a little bit. Okay, so this is as simplified as we can get it. So remember here, we want to set this equal to 0. Let's think about our denominator. Our denominator is never going to equal 0 because 3x squared plus 1, we're not going to find an actual value that gives us 0. So all we have to do is worry about setting the numerator equal to 0. So if I divide both sides by -6, I get 3x squared minus 1 equals 0. Adding over that 1, I get 3x squared equals 1, and I can divide both sides by 3 to get 1/3. And now I want to get x all by itself, which means I need to take the square root of both sides. So I get both positive and negative square root of 1/3. So let's go ahead and set up our number line. Okay, let's take some test values. I'm going to choose -1, let's do 0, and +1. Those are nice ones to plug in. And remember, we're going to plug that back into the highlighted form. So I'm going to go ahead and do that. So I don't care to solve this all the way. All I care about is that this is a negative value. So that tells me this will be negative, which means our function will be concave down. The nice part between -1 and +1 is that it's going to result in the same value, and that's because we're squaring both terms. So when we square -1, we get +1, so they're going to have the same outcome, right? Which tells me that this interval will also be negative, which means our function will be concave down. So now all we got to do is plug in that value of 0 and see what happens. Again, I'm not going to solve it all the way, but I notice that this is going to be a positive value because those two negatives will cancel out, which tells me on this interval, our function will be concave up. So let's go ahead and write those out all officially. Okay, so let's compare this to our actual function. So I have that graphed out right here. Let's look at our inflection points. So they're going to be really tiny. They're going to be right about here because they're less than 1. But let's look at our concavity. So first we have concave down on either sides of our inflection points, right? Which fits with our number line. But if we zoom in real close, we have a tiny interval where it's concave up. And that fits right with our number line. We have its concave up in the middle. So that one's a bit tricky, but it's there. Otherwise, that's all I have for us today. If you enjoyed this video, I have many more like it, so make sure to check out my playlist. They're linked down below. Otherwise, please give this video a thumbs up and comment other problems or topics you'd like to see done. Thanks for watching.